about this, let's go directly to Josephson Junction. So what is this? Why this is so special? It's very simple. It is a superconductor sandwiched with an insulator. So when Josephson, I was told that, I don't know if this is true, he was like 20-something in Cambridge or Oxford, I don't know, Cambridge maybe. He went to present his theory about this Josephson Junction, and the very person who got, I think it is Bardeen, was in the conference and does not trust him, and then challenged him in the presentation. And then Bardeen was saying that, and then he tried to say that, he tried to argue with Bardeen, and then I think it's Bardeen. If not, please forgive me, Bardeen. So, and then he was saying that, then the guru, right, is saying, are you saying that I'm wrong? And then Josephson said, do not force me to say so. I can remember this, what my TA told me when I took the quantum solid state class, right? So that just to say that the idea is very weird in the Josephson Junction. We know there is tunneling, but he proved that this tunneling is actually resistiveness, and then it has some very special property. Top is superconductor. For example, it can be aluminum, right? And then the middle one can be some non-stoichiometric aluminum. I still make it stoichiometric, right? Those people deposit aluminum, oxidize it, deposit another aluminum. Niobium is also something very commonly used. I think niobium has a higher TC. For example, let me just put here, niobium, NB, right? This is a very common one, but still use aluminum oxide. So if I apply a voltage across it, then it is called V. Now, do you remember I just said that this is a macroscopic object? So inside this superconductor, right, I have this ns e to the power I phi, right? I have a phase. It's a macroscopic quantum object. It has a wave function, I phi. So it can be that maybe on the top, this has the phase of phi A. On the bottom, this has the phase of phi B, right? And then we can say that the phase difference between them is phi A minus phi B, which is okay, right? And now we are not going to do the math. We just say that what the result it is. It has two equations. The first, Josephson's equation, I think it's called Josephson equation, is this. The current going through this device is equal to IC, which is the critical current, after which it is no longer superconducting. So there's a maximum current. We just told that there's a critical current density. For this one, correspondingly has a critical current, times psi phi of t. You see, the current depends on the phase difference. The phase difference of the wave function, not the voltage across it, okay? Then it has the second Josephson junction, second Josephson equation. It tells us that the rate of change of the phase depends on the voltage across it. So these are two important equations. I hope that you can memorize it. If not, at least you know that currents depends on the phase difference across it, the phase, not the voltage. But the phase is going to change depends on the voltage across it. Okay? Now, we will try to understand this equation more, but here I want to introduce a quantity. When you when you look at this phase change, it is the so-called magnetic flux quanta. So for magnetic field, it is also quantized. You cannot go to arbitrarily small. Just like photon, can you break the photon to arbitrarily small? No, at the end is photon, a unit of energy. Magnetic flux also has a also quantized, right? We call it magnetic flux quantum. It basically means the smallest magnetic flux you can have. What is magnetic flux, by the way? It's B times A, right? Magnetic field times the area, right? Magnetic flux. It is phi 0 equals to H divided by 2E. If I want to write at H bar is 2 pi H bar divided by 2E, because H bar is H divided by 2 pi, okay? And just as a note, if you read the paper, sometimes they define this phi naught as, no, sometimes, right? Sometimes. You need to be careful when you read this, right? As H bar divided by 2, which we call it the reduced magnetic flux quantum, right? So this is just all the convention. So when you read the paper or read the textbook, depends on what they are using, they have the same symbol. The only difference is one is divided by 2 pi. But obviously, they have two different names. One is called reduced magnetic flux quantum. One is not, right? So you just be aware of that and check it when you see this problem, okay?
Professor?
Yeah.
For when it says 2 eV, that's not electron voltage, right?
No, yeah. This is the voltage. How about I call this AB, VAB? Then this becomes VAB. Electron charge times the potential. Okay, it's not unit. Yeah, very good. Not EV. Positive E. I think it is positive E. Yeah, I think so. Yeah, because you see here, I also use E. So this is positive E. Right? It's not negative 1.6 times 10 to the power negative 90. It's 1.6 times 10 to the power negative 90. Now, so after we learn this magnetic flux quanta, what we get is just another symbol, which is useful. Let's look at the second Josephson Junction equation one more time. Partial phi partial t equals 2 pi v over phi, 0. Okay? So maybe a little bit too fast because I'm just doing what? 2e, or just use this equation, right? 2e divided by h bar. 2e divided by h bar is just 2 pi divided by phi 0, phi naught. Okay, I just represent everything as the magnetic flux quantum. Okay? Then what does it mean? It means V equals to partial flux, partial phi, partial t times this one. What did I say wrong? And then, sorry, I'm a little bit distracted. And then I introduce another symbol, right? I just keep doing the symbol. I just combine them together. Combine phi naught phi divided by 2 pi. Do you see this? I just say, oh, phi and phi naught divided by 2 pi. I just put them as phi. That's it. My only goal is just to show you that this is equal to partial phi, partial t. Is that okay? So what I'm doing is nothing special. All I have been doing is just to use the second equation. I keep changing variable. Of course, some of them has some meaning. For example, phi naught is the magnetic flux quanta. I keep changing so that I just group the whole thing becomes partial phi, partial t. Okay? This resemble what? Have you seen this before? Voltage is equal to d phi dt.
Lenz's law?
Lenz's law, right? Resemble that. What's Lenz's law? You build a magnetic field, and then when you try to change the magnetic flux, we will induce the voltage across the circuit, correct? Now, do I have any magnetic field here? Did I ever talk about magnetic field in the whole derivation? I did not, right? But I come up with a form that's similar to the Lenz's law, okay, or back EM wave. So it looks like I have inductance. Lenz's law is because your circuit has inductance. When you change the flux, you cause the change of the voltage, right? But here, I don't have any magnetic field, but I have the same equation. It means I store the energy in somewhere, and this somewhere cause an inertia. What is the Lenz's law, right? It's just the inertia. You store the energy in the magnetic field. Now you want to reverse that direction. You actually need to revert it because it has the inertia, right? So here is the same. But however, this is not the regular inductance. Regular inductance comes from the storage of magnetic field. This is called kinetic inductance. And one way to think about this is that I'm superconductor. There's no scattering. The electron, the Cooper pair will just fly. You are not going to stop that. They have this inertia. In a regular inductance, you just wait, they dissipate, and then the current will go. Now, if I have superconductor, I don't apply any voltage. I don't apply any external energy. The current, you just root forever, lock forever. That is the inductance, right? So instead of like in the regular inductance that you store in the magnetic field, here you store the energy as the kinetic energy of the Cooper pair. That's all I want to say. Right? Maybe I also don't understand this well. But the most important thing is you come up with an equation as if I have the inductance. And that inductance, regular inductance, that is kinetic inductance. And actually this happened in your regular device also, your LC circuit at room temperature. But it just turned out that the regular inductance is way larger than the kinetic inductance it has. So we never discussed this in our E class. But when you go to superconductor, this one pick up. Even this also has a regular inductance because any object that has a shape has an inductance, right? You just do an EM wave simulation in HFSS. You can always extract the equivalent inductance. But it has a larger inductance due to kinetic inductance. Okay, so a lot of change of variable, but the only important information is that voltage depends on a form like this, and it is already in the second Josephson junction, VAB proportional to d phi dt. Although phi is the phase, but it becomes look like a flux. And that is what we're going to use later to quantize the circuit also. You will start doing some flux flux quantization, or treat them as flux through this device. Is that okay? Is that clear? Yeah? Only thing is remember this, okay? Okay, so let's take a look. What is so special about Josephson Junction equation? Josephson equation. JJ equation. Josephson equation. Okay. If voltage equal to 0. If voltage equal to 0, then what does it mean? It means partial phi, partial t equals to 0, right? So then what does it mean? It means phi equals to a constant. The flux is not going, the phase is not going to change. The phase across the junction is not going to change. Again, what is phi is phi A minus phi B, right? The phase between the superconductor, let me show you again. This is phi A, this is phi B. Constant, they have a constant difference, okay? But then what is the current? The current is I equal to IC sine phi t. But phi is a constant, right? So as time goes by, what happened to the current? It's going to oscillate, right? So you never seen a device that you apply 0 voltage. So it's not oscillate. I say the wrong thing again. I gave the wrong equation. I'm sorry. What should be the equation? There should be no t, right? I'm sorry. Phi of t, but not phi times t, right? At the time t, sorry, right? So what happened to the current? It should be a straight line, constant. Low voltage, but you have current keep going, which makes sense. We're talking about superconductor, right? I think the first time they demonstrate that, they were able to bring a superconductor ring, I don't know, from a country in Europe to another country for the World Expo. And then it lasts for a few months, I think, right? So they will just keep circulating, which makes sense. Okay, then not very interesting. But if V not equal to 0, then now we have V equals to, I deliberately put this d plus dt, so you start embed this into your knowledge, which is just equals to the quanta or the reduced magnetic flux quanta times the d phi dt. Okay, here, right? d plus dt is not difficult to memorize. It's just equal to reduced magnetic quanta times the phase. Okay, so that's what I'm doing. This was the original Josephson Junction second equation, right? But I can write as d plus dt. Is that okay? Now, if it is not 0, but assume it's constant, let's say assume constant. Okay, I say, how about let's assume it's equal to V naught. How about this, right? If that is the case, what will be the phase? It's going to be equals to V naught equals to phi d first dt, right? And then you do an integration. It is equal to 2 pi divided by phi naught. I think I'm writing too fast. 2 pi divided by phi naught times V0 dt, right? Maybe it's integrate from 0 to a time t, for example. But because it is constant, then of course this is just equal to V naught times t, for example. Is this okay? Right? Basically, you just do the integration, right? You even don't need to go through this because you know very well already. If this is constant, then the rate of change is constant. Then the phi must change linearly. That's it. The rest is just some ugly math. So how would the phi look like? If you look at the time, I only want to look at the phi. The phase difference across the device, right? In this particular, say it go from 0, but you can have some initial condition. It just go up with a slope, right? And that slope is 2 pi divided by phi naught times V0. This is the slope, right? The phase difference keep going up. But phase difference, you can go up, not a problem, because once you reach 2 pi, its effect is the same as just keep doing modulus, right? The point is, what is the current now? What is the current now? That was the mistake I made, right? because currents now equals to IC times sine the phase. And the phase now is 2 pi divided by phi naught V0 times t. These are constant, and then you go with t, right? So you are going to oscillate. And what is the peak? IC. And IC is the critical current, which makes sense, right? So you do not think that you can go more than the critical current, because after critical current, you start breaking the Cooper pairs, you go back to a normal state, no longer superconducting state, right? And then your Josephson junction is not going to work as what you want. Yeah. So this is an important concept. Why this is one very important application is the definition of volt. How do you define a volt? Is that a frequency? It's volt. So if you go through the math, right? If you go through the math, you see that the frequency is oscillator frequency divided by the voltage across it is just equals to 2E divided by H. .83 times 10 to the power 14 hertz per volt. It means if you apply 1 volt across the Josephson junction, this current is going to oscillate at this 483 gigahertz. No, terahertz. 483 terahertz. If your voltage changes a little bit, this is going to change. Now measuring and you see that in this whole process, or if you have chance to go through the derivation, it doesn't depend on the quality of your Josephson junction. It doesn't depend on the thickness of the insulator. And even doesn't depend on the gravity or location or whatever. So this is a very good definition. And you can use it as a voltage standard. Right? So in the old time, before they have Josephson junction, I forgot they use other thing to define the volt, and everyone need to calibrate to that one. And now I believe that Keysight, when they do their equipment, I don't know if they calibrate directly to Josephson junction, but definitely it's indirectly to Josephson junction. Something calibrated to Josephson junction oscillation, and then all the way propagate to here. Okay? So that is one of the application. Any questions? F over V, okay. Good question, right? So I am a little bit rushed. This one is just equal to 2 pi F, right? Because psi something times t, right? That is 2 pi F. So 2 pi F is equal to 2 pi V0 divided by phi naught, right? Because this is the oscillation frequency, right? So it means V divided by phi naught equal to F. The frequency is the voltage you apply across the Josephson junction divided by this quanta, flux quanta, right? So that's why F divided by V equal to 1 over phi naught. And 1 over phi naught, I jump a little bit. 1 over phi naught is 2E over H. Right? And that's why I have 2E over H. And basically, it's just saying that for 1 volt, what the oscillation will be. If I apply 2 volt, the whole thing will be times 2. Okay? Good. Any questions? If no, we will keep going, right? We don't want to go too deep, but there's some concept we need to understand. We talk about inductance. We just say that it does have an inductance. But what is that inductance? What is that value? Not just that it has inductance, it has non-linear inductance. That's why I highlighted here. This is very important for the silicon, the qubit. We need non-linear inductance that will be clear later. So let's try to find its inductance. So let's do this. First, I give you I equal to IC psi phi. I hope that now you can memorize. I also gave you V equals to d flux dt, right? Where this flux is actually equals to, what's that? The quanta flux divided by 2 pi times the phase difference. This is what I defined, right, earlier. So I want to find its effective inductance. I just need you to recall how you find the inductance. The voltage equals to the inductance times di dt, right? One way to find the inductance is change the current at a certain rate, find the voltage, the ratio is the L. So that is my purpose. So let me look at di dt of my equation, right? So I'm going to use the chain rule, di dt equal to d phi dt and di d phi and then d phi dt, right? Again, phi is the phase across the Josephson Junction. Is that okay? This is just only a mathematical tool. My goal is to get the IDT in terms of V, and then the proportional constant is L, right? So I get the IDT, but I don't know what is the IDT because this phi depends on here. So I break it into two parts. DID phi is easy. What is that? What is DID phi when you plug in? DID phi. What is that? Thank you. IC cosine phi. Right? A very simple one. How about d phi dt? Okay, this is also easy because I have the second rule, right? So actually, this one is not easy to see when I try to put that, but I do want you to see the d plus dt. So I just plug in, this becomes phi naught divided 2 pi d phi dt, right? This was the original Josephson Junction equation, but I deliberately put this into the phase, so I have a flux. So now let's go back to here. So what is d phi dt in this case? Right? This one is simple, right? d phi dt is equal to V divided by phi naught divided by 2 pi. Is this okay? d phi dt equal to V divided by the whole thing. Right? The whole thing. This is V equal to d flux dt, right? Or the original form is actually V equal to magnetic flux quanta divided by 2 pi, which is the reduced magnetic flux quanta. That's why people sometimes want to use the reduced version. It's easier to write. I just put this low 2 pi. And then d flux dt, right? So d flux dt, d phi dt, not d flux, sorry, this is d phi. d phi dt equal to V divided by the whole thing. Okay? So I group the terms. What do I get? I get V. And then I want to put everything downstairs. Okay? So it becomes phi naught divided by 2 pi. And then the whole thing IC cosine phi. Right? A little bit ugly. But you see what I'm doing is V, the denominator and numerator divided by IC cosine phi, and I keep this one here. Oh, is that okay? I just rearrange the terms. Right? The main reason is this. Now, I have V here. I have di dt here. So then what does it mean? It means L equals to phi naught divided by 2 pi divided by IC. Then the whole thing divided by cosine phi. Okay? Because V divided by L is di dt. Here I show that di dt equal to V divided by this L. This is L. This whole thing is L. Okay? Now I will going to further simplify. I'm going to call this Lj, and then the whole thing divided pro sine phi. Okay, because sometimes people use this symbol Lj to represent this Josephson Junction inductance when the phi, which means the phase across it, is 0. So that's why you see this one is nonlinear. It depends on the phi across it, cosine phi. Phi naught is the magnetic flux quanta. It's constant everywhere in the universe. IC is the critical current of your device. It's constant for your device. But phi is not, depends on your operating condition. And you have cosine phi. Definitely is not linear. The conductance, the inductance is due to this one. Again, what inductance is this? Is that inductance due to the energy in magnetic field? Due to kinetic energy. Very good. So this is the kinetic inductance, right? So in case you have some very lousy or some very special Josephson Junction, you have also the magnetic inductance, then you need to add that, right? Here is purely kinetic inductance. So that is the first thing, Josephson inductance, right? So good to know how to derive, but after all, it's just I want you to accept that its inductance is Lj divided by cosine phi. This is you going to use in the circuit analysis later. Okay, if this was even lower level class, I may just give you L equal to Lj divided by cosine phi, right? You just take it for granted. Okay. Then another thing is Josephson energy. Now you start having some relationship to your project, right? In your energy participation ratio. Maybe you still don't know exactly what's going on, but we do know there is something called EJ in your part 1. And it compared to EC, they have different things, right? So EJ is the Josephson energy. So what is that? It's the total, because it has inductance, then of course it stores energy, just like the magnetic field. So a Josephson Junction does store some energy, but store as the kinetic energy, right, of the Cooper pairs. So let's see what energy it has, right? So it's just like capacitor and inductor, just like inductor, right? It's not resistor. Again, it's always good to memorize this equation. IC phi, Josephson first equation. Second equation is V equal to d flux dt. And do not forget, so-called flux is just equal to reduced magnetic flux quanta times the phase across it. So how do we find the energy of a system? It's very easy. We just say, okay, energy must depend on the initial and final state, right? For example, you find the energy of a capacitor, you try to charge it from 0 to V, and then you find how much current go through. And you go through this integration process if you have done that before. If not, that's okay. We go from phi 1, initial state is the phase difference across the Josephson Junction was phi 1. And then we do something, it becomes phi 2. In this process, of course, you have the current going through, you have the voltage across it, this gives you the power, right? IV dt. And these are not dissipative power because this is a superconductor. So all this energy will be stored in Josephson Junction, just like capacitor. Just like I give you a capacitor, maybe inductor is even better. I start from 0. And what is the energy? Well, I start from 0 charge to V, then IV dt, of course, will give me the energy, right? And then, if you remember how to do it, I forgot how to do it actually. IV, right? It depends on the relationship between I and V. Of course, you have the capacitance. I equals to what? I equal to dq dt, right? And V equal to C equal to Q over V. So V equal to Q over C dt, right? That's why you get dt cancel, equal to 1 over c. And then you integrate q is q squared divided by 2. And that is how you get the total energy, right? Of course, you can convert q to v, which is cv equal to q. That's why you got half cv squared, right? That is good. I asked you, what is the energy in a capacitor? Half cv squared. How do you get it? You prove by doing current going through the voltage, right? Same here. What is the energy stored in the Josephson junction? Current times voltage dt, and then from its state go from phi 1 to phi 2, right? We are not talking about the voltage, right? Because the state variable is the phi 1 and phi 2. So we keep doing, then of course, this equal to what? V dt. V dt here, right, is equal to V dt is equals to this magnetic flux constant d phi, right? Because V dt equal to d flux, V dt become d flux, and d flux is just equal to phi 0 divided by 2 pi d phi. Correct? And then, of course, I know I depends on the, it should be sine, right? Sine phi. Do you see this? Right? I just put in I, because I is IC times sine phi. Right? So now I can do the integration. This is a constant. I take it out. IC phi 0 divided by 2 pi. And how do you integrate sine phi? It becomes what? Negative cosine phi. And then you put in phi 2 and phi 1, right? So it becomes cosine phi 1 minus cosine phi 2. Right? If we assume phi 1 equal to 0, right? We assume it starts from the beginning, because only the difference matters. Then this becomes the energy, Josephson energy. No, this is wrong. I cannot say that. The total energy equals to IC phi naught divided by 2 pi, 1 minus cosine phi. I will just call phi equal to phi 2. Okay, just give a state, right? And we commonly write this as EJ divided by 1 minus cosine phi, where EJ is the Josephson junction energy, equals to IC phi naught divided by 2 pi. Okay? So I derive all these things just to tell you that this is a Josephson junction energy. Yeah.
Why phi 1 equals to 0?
No, I just start with, you can have other value, but I can just choose it to start from 0, because I only care about the difference from the first to the last state, right? How to say? Yeah. Then from here, you can also find that the Josephson junction inductance is equal to phi 0 square divided by 2 pi square times EJ. Right? I don't think you need to memorize this. Maybe I will give you if I need that. But I just want you to know that the Josephson inductance has some relationship with the Josephson energy. Right? But the most important is that we have a Josephson energy, EJ, times 1 minus cosine phi. Is that okay? It's just like the capacitor, half CV squared. C is the characteristic of the capacitor. EJ is the characteristic of the Josephson junction. You have IC phi naught. IC is the characteristic, right? And then it depends on the phi.
For the sake of questions like on the test or homework, can you just assume that that's you ever get to
Yeah, unless I say no, yeah. But here is the proof. Actually, from now on, you will just use this as the Josephson energy. And yeah,
So yeah.
in general, that's what you get. Yeah, this is just the proof. And then, because I think, how to say, and then from here, EJ is a constant. In some paper or textbook, you will just remove this one, becomes negative cosine phi EJ. Because energy is just a reference, you can always change the reference of your system to make things easier. So sometimes people just say the Josephson energy is EJ times negative cosine phi. Okay. Great. So